All right, that's time. Perfect, thank you. All right, so thank you for coming. Welcome here, we got a packed house. Today we're talking about comonads, which of course are comonads in the category of interfunctors. What's the problem? Thanks to Wire, I work at Wire. They helped me come on out here and they're kind of supporting me while I'm doing this. And we are hiring for Haskell jobs and DevOps. So check out wire.com/jobs if you want to work in Berlin and do some Haskell. So. Cool. So the rough outline today is going to be this first session here. We're going to go through what comonads are, of course, very helpful. And we're going to explore some of the use cases of comonads over the stream comonad and see some of the things that we can actually do with it in a very concrete way. That's a theme for the rest of the talk is we're going to explore some abstract concept and then we're going to try to build an intuition for it by actually going through real examples that at least kind of make sense. So this is mostly a theoretical talk in that we're exploring this kind of abstract type class of what a comonad is. But we're going to try and relate it to real-world concepts, so maybe you can find a spot in your work or in your code base that can be expressed as a comonad, and you can explore that on your own, and you feel comfortable doing that. We're going to get into the store comonad after, and then if you don't know what that means, it's totally fine. Tomorrow, we'll get through a couple more of the comonads in the comonads library, and if we're lucky, get into some really cool stuff. I mentioned earlier, if you like, you can grab the source for this. It's also at the bottom of the screen here, really small. If at any point during the talk you want to check it out. It's not necessary, strictly speaking. We will have all of the examples that we go through are in there, so you can check them out later. You can play with them at home. I like to make sure that everybody's kind of engaged and following along, hopefully. So I do like to have kind of a more interactive talk format. I'm not just going to stand here and talk for 2 hours. So what that means in this case, because it is mostly like a slides-driven talk, is if you do get lost, feel free to throw your hand up and say, hey, what's that thing? Or if maybe it's quite possible I missed explaining something because I'm used to it and you're not. So feel free to just say, hey, what's that thing? What's that notation? What's this going on there? And we'll try and work through it together. Maybe we'll backtrack a little bit. Better to spend a few minutes backtracking than to go for 2 hours and lose everybody, right? So if we get too many questions, I might kind of just try and keep it on track, or I'll say, hey, talk to me, after the session or something like that. Just respect that. But cool. So I think it's really important when we're at these things that we actually get to know some people. So I'm going to give you 1 minute. If there's somebody next to you that you don't know, maybe just like say hi, get their name. That would be great. Now you have someone to bug and ask questions. All right, 10 seconds. Okay, thank you, awesome. There will be a quiz on that afterwards, so hopefully you know everyone's name now, right? Everybody's got it figured, solved? Okay, so hopefully most of you have at least heard of this concept of monads, which we all know are burritos, right? So that means comonads must be taco salad. Welcome to my TED Talk. You can all go home. Basically, we want to introduce comonads roughly related to this concept that we already know, but the co part in front basically means it's the dual of monads, which means it's opposite in some way, shape, or abstract form. It's the upside down of monads. So in order to introduce comonads, we can actually talk about how they relate to monads and how they flip these ideas on their heads. So monads introduce effects. Hopefully everybody's familiar with that. Here's a monadic computation, right? Put stir, it takes a string, and it creates this effect where it prints it out to the console and doesn't return a real value. It's basically a strictly effectful computation. Here's another one. Read a file. Oh, my slides died here. That should be IO of a string. Words doesn't really look like an effectful computation, and most of us wouldn't think of it as one, but as we can see, it actually still matches this pattern of taking some value and introducing some context around the output. So most of us don't consider lists in the view of a list monad, but they actually are. It's adding some context to the string, which is, oh, hey, there's more than one of these things. So we can also talk about effects like this. So this whole thing is an effectful computation. Find takes two arguments, and then it returns some value inside some context. In this case, the context is, well, did we find the thing or not? Is it there or is it not? And we can actually make this match the same kind of format if we just take a tuple of these two things. So by currying and uncurrying, we can force it into this form where it takes a single argument and returns something that is effectful. So we can kind of see that, monadic effects add some context to our calculation, and they all kind of fit this format here. So these are called also coalgebras. They introduce an algebra into our system here. They introduce some context, some container. So what about co-effects? I feel like this is something that sometimes people will ramble on in a Reddit comment and you kind of pass over it and you're not really sure what they're talking about, but you smile and nod just like everybody else. But let's actually dig into what that is and what that means. So when we're talking about it basically means we just flip all the things. All the arrows get flipped on their heads and we can see what it kind of looks like. So here we're flipping this into the upside down. We've got our effectful computation. It introduces this effect. And we've flipped it all over, and we've also flipped this arrow backwards. So now we had a A to an M of B. Now we have a W of B to an A. Do you know why it's a W? We flipped the M. It's great. Okay, can't make this stuff up. Okay, so if we normalize that into our standard notation, we flip the arrow back, we rewrite it, well, we can basically express it like this. So rather than introducing some effect into our computation, we're actually removing some context around this value and resulting in some new value. Can everybody see the screen with the lights on? Okay? It's okay? Yeah, I think so. It's big text, so it should be okay. Good. So co-effects are basically queries over some structure that reduce it down to a single value. So given some structural thing, I can produce a single value. And they have this form of the WA to B. And we can also call these algebras. They reduce some structure down, but there won't be a quiz on that one at the end. So let's look at some queries, I'm going to call them. That's actually a term I'm going to try to kind of coin for Comonads during this talk. We'll see how it goes. That I borrowed from Isovector. Sandy McGuire came up with that idea. So here we're using length over some structure, right? So in this case, the list would be the W. It's a quirk of Haskell notation that it's not written that way, but we can imagine that this is a W of A's where the W is list, and it returns an int, which would be the B at the right-hand side. And we can think of this very much like a query. It's taking some structure, and it's telling us something about that structure. It's telling us how many A's there are, right? So here's another query. Given some context of A's, we can say, oh, what's the first one, right? And the idea of there being a first one is dependent on the context. So you can't say, oh, what's the first thing in an IO of A's, right? Like, it doesn't really make sense. It's a contextual operation. In this case, because list means we have many, we can talk about there being a first one. Okay? And we can do the same thing as we did before, where we can actually take more than one argument, and using those arguments, construct a query-like contextual reduction like this. So in this case, we're saying, oh, I want to check whether I have an element. So let's say if we have an element A, then we can build this structural query, which says, do we have that A inside this list? Is that all making sense so far? So far, so good? Yeah? Yes? Yeah, great. Okay, awesome. talking to a wall here. This is great. Okay, so we can have some other types of queries too, which actually depend on the context itself. So before we had, get the first one of the A's, that one is actually just pulling one of the A's out of the structure, but we can actually ask about the structure itself. So if we were to put this in the form of a W of A to B of some kind, the W would be tuple of A. That's kind of the context that's around our thing here, right? And we can actually ask, what's something that's in that context? And we can get the A out. Or if we want, we can get the value out by using second here. So tuple is actually, it does have instances for both monad and comonad, depending on the restraints that you have over the first part of the tuple. Yes, so tuple is the writer monad in disguise. Typically you would use a new type over it, but it only works if the first element is a monoid. So you can check that out later. And it is, as we'll see in the future, it's actually the env comonad as well. But again, there's different requirements on each of these. So yeah, good question. Okay, here's another query. Now we're not talking about lists. Now we're talking about some other context. We can talk about a tree as some sort of structure. We can say, oh, given a tree filled with numbers, I can sum them all together and get some results. So this is a query that actually does look at the entire state of things and compute some result. And this is a query, this is a co-effect. They're the same thing. So we kind of understand now how monads introduce effects and can talk about this idea of this structure that they're introducing. And comonads do the opposite. Well, monads also let us compose effects, right? So bind and those double arrows that we use when we're just printing stuff to screen, that composes I/O effects. Since monads are a context where we can introduce effects, comonads are a context where we can run queries. So just like in a monadic context, it's not just that you can only run one of those monadic operations, right? You can do several of them, and you can chain them together, and you can feed the results of one into another. Comonads are the same with co-effects. You can run one query, and then on the results of that query, you can run another query. And then on the results of that, you can run another query. But it's not exactly clear how that works, right? Because we're discarding this structure. This list is now gone, and we've summed it together. So what does it mean to chain another query onto a single element? We have to get it back into that structure somehow. So let's add some context. Let's look at an actual real-life data type that really does exist. This is a definition stolen straight from the streams library. This is an infix data constructor. If you guys haven't seen this before, it basically is just, oh, this is a data type that has two values, an instance of some A type, and another stream. So when does this stream end? Anyone know? No, never. Doesn't. Goes on forever. So now this is another stream. We got another A, we got another stream. We got another A, we got another stream. Goes on, loops forever, yeah? Okay, cool. So we got this type. Not important. I'm going to implement functor and foldable with my beautiful programming style right there. Let GHC do it for me. And we're going to define these helpers. Don't worry about the implementations. I've got one that can turn a list into a stream. It's partial, but whatever. It's just for a helper for the talk. And it'll just cycle all the elements in that list. Good to go. And with it, I'll just I'll build this count stream, which is an infinite stream of numbers that just counts up. We're going to use that as we go through the talk. Yeah. Cool. Questions on the helpers? Should be hopefully good? Yeah. Okay, great. So let's write some queries. So we have this new data type, which represents a context. What are some things that we would want to do with this stream? Well, one thing that we can do is we can say, oh, I want to get a specific index. So this X is just short for index. Don't get it confused with the one from the Lens library. I'm just making this up here. And it says, okay, well, which element do you want? I want the 5th element. I want the 7th element. And then if you have a stream of A's, I can actually get that element. And you'll notice this doesn't need a maybe because the stream is infinite. It will for sure have a 5th element, guaranteed. So this, like I said, we can actually imagine that these are paired up in a tuple and say that this is, or rather it takes some configuration for our co-effect. And once we've configured our effect, or our query, then we can reduce the structure of a stream down to a single element. Okay, so we can implement that. It's really not that interesting. We just kind of recurse on the list. And once we hit 0, then we pull the element out. Just like you would write it for a list. OK, cool. So let's look at our first real example here. We have this count stream. And we can get the first element out of it. We can get the second element out of it, or I guess that's the third element, technically. And we can get the 1,337th element out. Nothing too interesting. OK, so does anyone have questions about the data type that we've set up or any of the helpers so far? Yeah?
I have a question regarding the use of the word effects here, because I feel like in most of the literature that's out there, effects are seen as a sort of thing where the code is sort of interacting with the outside world in some way.
Sure.
Where in this case, we're talking about it in terms of you're sort of hoisting a value into a structure.
Yes, exactly.
So is it typical to talk about effects in the way where it's not actually doing some sort of async or I/O, and it's actually just lifting something into a structure? Or
so it's
kind of new for me.
Yeah, sure. It's just kind of semantics, right? And it depends on how you, I kind of interchanging the words contexts and effects here to mean roughly the same thing. But I think we talked earlier about kind of effectful algebras, and so this can, you can think of it that way. But that's why I had those examples kind of demonstrating like, oh, a list can be considered some sort of context or some sort of effect. Yeah. So, yeah, don't let it hang you up too much. Right on.
Maybe a dumb question, but why isn't count stream just evaluating infinitely?
Because I hacked the show instance to only show the first 5 elements. So it would, yeah, if you tried to show it on your screen, it would loop infinitely. But I'm just trying to represent this is an infinite stream, and we can still work with it because Haskell is lazy, so long as we don't try to evaluate the whole thing.
Okay, so your show instance is just taking.
Yeah, exactly. So the real show instance will crash your computer. OK, so what? We have this index function. What do we want to do with it? Well, now let's say we have this query. We actually want to write a different sort of operation. So, OK, I can get the 5th element, but what if I want to look at the stream that's starting at the 5th element, but still has the rest of the stream there? Okay, so I'm going to call this drop s, just so it doesn't drop stream. It doesn't conflict with the prelude, and it actually looks very similar in the signature, right? It's you set it up, say, oh, I want to drop 5, takes a stream. But instead of getting a single element, it actually shifts the entire stream along into that 5th element. So you can see that these are related, but not exactly the same. And we'll see exactly how that relation ties them together in just a second. So here's what it looks like. Again, count stream. We can drop 1 element, and we see what that looks like. And we can drop 2 elements, and we can see what that looks like. That's basically how you would expect. It's similar to lists, yeah. So what I'm going to call this, don't get hung up on this name. I'm going to call it a mutation because we're changing from one sort of structural context into another structural context that has been altered in some way. It's still immutable data structures. Don't worry about that. It's just a fun word for what we're going to call this. So it's not mutating any memory. It's still immutable data structures. It just kind of seems to match that sort of idea, right? So if you drop 5 from something, it still seems like the same stream, but it's changed in some way. All right. So what are some other things that match this kind of mutation style signature, where we can imagine it as a W of A to a W of B, where we keep the same structure, but we've shuffled things around a little bit. So if we have a Gaussian blur, that's kind of it's a Photoshop thing where you actually, for each pixel, you average all of the surrounding pixels, and then you put it back where that pixel was, and you do that in every spot in the image, and you get these cool blur effects, right? So really, that is just going from an image to an image, but it's rearranged the contents in an interesting way that has blurred all of them together. So that would be kind of a mutation. We can also say, well, given a graph, I can follow this graph, this series of edges through the graph, and end up at a different position in the graph, a different view of the graph. It's still a graph, but we've kind of mutated in some way. Maybe we don't even have access to the whole graph anymore. Okay, and here's another slightly more abstract one. We can do a scan. So this is the definition of scan L1, which says, oh, okay, given some way to combine our accumulator, we will go through this list and rewrite it, and rewrite the contents as we go. But we still end up with a list at the end of the day. Okay, some more examples. You could, for instance, throw away the top value of a heap, and it would presumably restructure itself. If we had a spreadsheet as our structure, we could actually say, oh, well, let's delete a column from the spreadsheet. You still end up with a spreadsheet at the end of the day, but we've reshuffled some of the values around. And here's a little bit more of an abstract one. If our context that we're dealing with is actually a function, okay? So this W of A, where W is, you know, the double with the arrow, right? So it's kind of a reader monad style thing. If we have a function from double to double, we can compute a new function from double to double that's the derivative of the original. So this is kind of the idea of taking something, reshuffling everything, but still keeping the original context. So this might be a little bit confusing, but we'll get deeper into it, of course. I'm just trying to tease for later sessions. So other things we can do with this sort of contextual operation, just 1 second, is we can solve hill climbing problems in like optimizations. We can compute the roots to Newton's method, and we can actually solve multiple iterations of Newton's method over functions. We can compute dependency trees for things, and we can actually solve Google's rainwater problem in a really elegant way. Okay, you had a question?
Yes, sorry, my confusion, but why are you calling this mutation? It seems like a functor, because you are preserving the structure.
Right.
But changing the...
Right. Okay, that's actually a fantastic question. So the interesting thing about a functor is that you can only change the contents, and you actually can't move the contents from one spot to another, right? So if you fmap over a list, you can't actually sort the list while you're fmapping. It's not possible. Whereas this sort of thing doesn't quite have that constraint. It's one layer up. So it says, oh, I can take the entire structure with some values and return a whole other structure of values you could potentially sort using a mutation. Yeah. Okay. So this is what we have. We have this operation that can, you know, get the third element or whatever, and we want to get this other operation where we move the stream along by that amount. These look really similar, right? Like they're close. We're just, oh, we're missing some context here. But they don't really seem actually related at a functional level. Like, how do they relate to each other like that? Can we turn one of these query operations into a mutation level thing where instead of just grabbing an element from there, we actually shift the entire stream? Spoiler alert, yes we can. So back to monad, we have one of the nice little monad functions called join. And join does this thing, right? So given a nested set of these contexts, we can flatten them down into a single one. And the way that we do that is completely different from monad to monad, but there's laws and all of that stuff, which make it convenient. So do we have a cojoin? What does this even mean? We flipped all of the arrows, and now we can go from an unnested value, and we can nest it. Okay, does that mean anything? Is that interesting? Sure it is. What is cojoin? Well, when we're talking about Comonads, we call it duplicate, okay? Because it's duplicating the structure. And we'll see exactly what that means as we go through an example. So the intuition for duplicate is a little bit tricky because we're not used to working with this. We're used to working with monads where, you know, you just flatten things down. Duplicate nests your structure within itself while maintaining some context or some sort of intuition about the structure. This is too abstract for us to understand, just like monads are really hard when you're only staring at the type class. You need examples. So let's go into some examples. With a stream, the kind of context that we're dealing with when I hand you a stream is your position in that stream. So if I hand you the count stream, we start at 0, and we can view all of the numbers counting up from there, right? But I could also imagine the idea of throwing away the first 5 elements and viewing the stream from the 5th element, where we can see 5, 6, 7, 8, 9, 10, whatever, right? So we have this kind of idea of a position within our structure. And in the case of a stream, each position is one of the slots in that stream, right? And we can actually pretend that we're viewing the an entire structure from each of those slots. So if we talk about duplicate going over a stream, we start off with a normal stream, and then we end up with a stream of streams. So there is, of course, a trivial implementation of this where you just put the entire stream into every slot. But of course, that's no good when we look at our laws. So how do we make a law-abiding version of this? We'll look at the actual laws later, but the idea is that each, so this is our normal simple stream here. We've got an A, a B, presumably a C, D, E, F, G. And each of these nodes kind of represents a position. So we're starting off, we're at this A node, and we can see the entire rest of the stream. And so when we duplicate, we put the entire stream viewable from A into this new node. So this entire box is a single slot in our resulting stream that happens to have a stream inside it. Okay, this is where it gets pretty tricky. It gets a little bit confusing. At the next slot, we've moved our focus to the slot that we're duplicating. So now we're focused on B, and from this slot we can only see B and the elements forward. And same here, we have focused on the third element of the stream, and we can only see from the third element forwards. I know you guys have questions on this one. Anyone? No? Awesome. Okay, so the idea is now we have a stream of streams, but we kind of have this intuition that each stream is like now focused on the matching element for that spot. Okay, so here's what it actually looks like, real code.
I have a question. I believe it's like the tails function.
Yes. Yeah, exactly. Perfect. Yeah, so it's like running tails on our stream. So we've got our count stream, and we run this duplicate on it, and now we can see, oh, in the first slot we have the original stream. Second slot we have it shifted by 1, and so on.
So could you say that the duplicate count, because like I mean count stream is like a countable infinity.
Yes.
Would you say that the duplicate count stream is an uncountable infinity?
I wouldn't say that, because I don't know enough about such things to talk about uncountable infinities. Yeah, I'm not sure. I mean, it's bigger than the other one, I suppose you could maybe say. Laziness makes all of those things kind of, less relevant, luckily, because I don't want to think about infinite streams. So yeah, so when we duplicate, we see that we create all possible views of a given structure. So if you just have a single stream, you have one view from that root, but you can imagine all of the other views where you view it from every other possible root. And yes, you're only viewing part of the structure, you're losing some of it, but that's okay. That's baked into the semantics of the data structure. So other ones can see the whole thing. Yeah?
Is that true for every Comonad duplicate instance, or just for stream?
So the intuition holds. So sorry, what exact point are you asking about?
For any given Comonad,
yeah.
Would that be a valid statement about its duplicate function?
That it shows us all possible views of a structure, yes. I would say that holds. Yeah. And that's codified in the laws, roughly, which we'll get to yet. So each view appears in the slot according to some intuition and some laws, which I promise we're going to talk about real soon. So the idea is that each view of the structure that exists is related to some slot in that structure, one of those A's, and when we duplicate, it puts that view into that slot. Okay, super abstract. So we're going to get through some more examples yet. Okay, so this is basically the same thing, right? We're thinking about each slot, and as we go, sorry, those numbers kind of shifted around. Okay, any quick questions here? Doing okay? Awesome. Got lots to get through, sweet. So this index function, it focuses a slot within the structure, right? So we have an infinite amount of slots, but with this index function, we can say, I want the 5th one, or I want the 6th one, and we can use it to identify a specific spot in the structure, and because we can select a slot in the structure, we can select a view of that structure, because each slot corresponds with a view. So duplicate fills each slot with a copy of the stream viewed from that position. And if we duplicate to get all the views, and we can use this index function to get a view, then we can use index with duplicate to implement drop. Okay? Let's see how we can do that. So if we've already duplicated our stream, well, now we say we want to pick the third element, 0, 1, 2, or whatever. Oh, actually, yeah, this is incorrect. Imagine that this started at 0 and so on. Sorry about that. I'll fix that in the slides later. But it does, trust me, it does the right thing. So it'll grab the proper element from the duplicated stream, and it will pull that out. Now, it's not just chance that this happens to also be the result of calling drop2, right? And in this case too, it will do the same thing, and it'll pull out this duplicated value that's at the right slot. So given something that actually takes a structure and reduces it down to a single value, using duplicate, we can run it over the duplicated structure and still end up with a structure at the end of the day. I think that's pretty cool. So this allows us to take some contextual focused operation and extend it through the entire structure so that it happens in all places at all times. Okay, so this is a possible implementation for drops in terms of index. Sweet. Any questions about how that works? Yeah.
Well, I have a question because for monads, I think there can be multiple instances, like for list or normal list node and zip list node. Is it for Comonads the same thing?
Actually, that's a really good question. I haven't come across any, but I'm pretty sure that the same exists. But you would have to consider the laws and make sure that you're adhering to them. But that's a really good question. I'll maybe look into that later today and see if I can find some. I'm sure some exist. Cool. Let's actually skip past it. So there's more. Can we go back the other way? So we've taken a query that, are y'all familiar with kind of what I mean when I say query now? Yeah? Kind of taking this context, squishing it down to a single value? Okay, so index is a query, and we managed to lift that up into a mutation where we're kind of shuffling around this entire stream. What if we want to go the opposite way? We have some way to edit the entire structure, but we want to turn it into a query that compresses down to a single element. So let's assume that we've implemented drop this time in a different way, and we want to get index instead. Okay? Let's see if we can do that. Okay, so again, structure is still very similar. Now we're going this direction. Okay, same kind of idea, you know. We can see, okay, if we drop one from the structure, we can see one is at the root of the list. And here, if we, get the first element here, well, we want to get this one. So how do we turn this into just this? And how do we turn this into just this? Well, it looks trivial, right? We want to get the first thing from the element. But in order to do that, well, we kind of need index to get it out, so we end up in this infinite loop, and that's no good. So we need to split this out and say that this is special, okay? So we kind of have this intuition that it's special because it's the root of the stream. It's a little bit unique. It pulls out the slot that our structure is focused on. So whereas index can pull out an arbitrary slot, this one is pulling out the root of the tree, the focused slot. We give this a special name. We call this extract. Okay? And this is a very, very simple query, which, given a stream of A's, always returns an A. And there's the rule that it must be the A that the structure is focused on, whatever that means for our comonad. So in the case of streams, the focused element is the root. Okay? Great. So if we define extract to be basically index of 0, but we would implement it this way so that we don't get that infinite loop, then we can say that it's this null op query, right? It doesn't really do anything. It just pulls out the top value. Okay. Now we can write this implementation where we first shuffle the entire list, and then we pull out the new value that we focused. So we've kind of realized that this thing can go either way. We can lift up a query, or we can squish down a mutation, and we can end up in the same spot. It's kind of cool. Okay, let's get to those laws that I talked about. Actually, before we get into that, questions about moving between queries and mutations and using duplicate?
I have a question. All your examples deal with local queries, but you have mentioned that there is global queries like length, and I cannot imagine how can go from the global query to the mutation.
Okay, so basically with Comonads, there's a rough idea where each Comonad could be described as using kind of relative position or using absolute position. So something like a spreadsheet would be an example of a global position, right? A cell index, A2, is not relative to anything. It's global to the entire document, right? And so as we get into those sorts of things, and some of these function ones, right, like you can say, what's the function value at x equals 40, and that's a global thing. So we'll actually see each comonad kind of has its own feel or its own kind of intuition about whether it does things relatively or whether it does things globally. So we will get to some global ones in a bit. Cool. So, laws. I have translated these laws into English, which is convenient because that's the language I speak. We can say that one of the laws is the original view, so the value we're passed, of the structure must be stored in the focus slot after we duplicate. Okay, so what that means is when we have this stream, if we're going to duplicate the stream, the original one that we were passed should be at the root of the stream. Okay? And that's witnessed by this law here. If we duplicate and then we extract, we should get the same thing. So if we duplicate the whole structure and then we pull the root back out, we end up where we started. This is true of all comonads. The focused slot of each view, so in this case the root of the stream for each of the possible roots, must match the value of the slot that it's stored in. So this is kind of a generalization of the previous. It looks very similar, except you'll see in the previous one we just call extract. This one we're f-mapping extract. Okay? So we're saying, okay, not only does the first one have to match the value we were passed, actually everyone has to stay the same. So if we duplicate and then we undo the duplication, we end up back where we started.
Does that imply that every comonad is a functor?
Yes, every comonad is a
So
functor.
it's not like every comonad is co-applicative is co-functor, similar to how the monad stack works.
Yeah, so cofunctor is not really a thing. There's contravariant, but it's not the same. So we don't really talk about cofunctors, but we do talk about, well actually, so the co of functor is functor, which makes sense why functor is also part of the type class hierarchy for a comonad. And there's a rough idea of a co-applicative. There's a similar thing in the comonads package called apply. And it roughly contains the same laws. If something is both applicative and has apply, then they must be equal. So you can kind of see a comparison there. And lastly, if we duplicate the outside structure and then duplicate it again, it's the same as duplicating the inside of a structure and then duplicating the outside. That one's not super intuitive, but it's still a law. It's still important. Okay, so here's actually the class. So you can see it's got a functor constraint, and we can make a comonad out of it. Here are the things that we need in order to work with these. We have this extract, which is the null query. It just gets out the thing that we're looking at. We have this duplicate, which we've looked at a lot, and it kind of duplicates the structure. And it has this other one called extend. And we were kind of sneakily using extend to implement those functions where we implemented drop in terms of index and vice versa. What it does is, behind the scenes, it will duplicate the structure, then run this function by f-mapping. Okay? And it'll end up here.
You can call it a co-platform.
Yes, so extend is co-bind. That's right. Yeah. So these all line up to extract is co-return, duplicate is co-join, and extend is co-bind. Yeah.
So the functions are inspired by flipping the monad.
That's right.
Right? Did you do the same for laws then? Is that
That's a good question. I would have to double check whether the laws are actually just inverted, but I would suspect that they are. Yeah, I think so. I think if you replace every instance of duplicate with join, and the same with all of these, I think the laws stay the same. Don't quote me on it, but we can check that after. Cool. And we can see here that we actually only need to we must implement extract, but we can implement either duplicate or extend, just like in monad where you can implement a subset of the combinators and it can figure out the other ones. They can be implemented in terms of one another. Yeah.
So new to category theory question, just to make sure, and if I'm off topic, I can take it offline.
Okay.
So it seems like at least duplicate is a natural transformation. Is the same true for extract? Does that make sense?
So duplicate isn't really a natural transformation because a natural transformation has to go from the same internals to the same output of the internals, right? So for all A, f of A to f of, or g of A. And in this case, the inside of the result actually depends on the structure in the first part. So it's not quite a natural transformation. Yeah. So that will not follow the laws. So yeah, not quite true. Yeah. Cool. Okay. So we've kind of come up with the intuition. Let's see how much time we have. We're doing okay. That comonads are structures or spaces. In a rough idea, the streams makes that pretty clear, I think, right? Like, you know, we have these slots and this kind of physical-like structure. It's easy to think about. And we can view this structure from different focuses. That's kind of the key intuition here. This view can possibly be incomplete, actually. So with the stream, you know, we start viewing the stream from the fifth element. We've kind of forgotten about the first four elements. That's okay. It's fine. It's part of the semantics of that comonad. The absolute positioned ones can always view the entire comonad at all times. The relative ones sometimes can't. And this is fine. So let's look at some actual comonads. So we did streams. We won't dig into super deep what all of the intuition is for these, but let's cruise through some so that we get a rough idea. So trees are also comonads, so long as it's a non-empty tree. So as long as you have at least one node, then it's a comonad. So these nodes are slots. The views are subtrees. So if you think of a stream as a tree, it's actually quite similar, right? So you can say, oh, this is a view of the tree where I can only see the children. I can't see the parent or the other siblings. And we can extract the root of the subtree, just the same as with the stream. Spreadsheets, I mentioned we have a focus. You can see it here with this nice little blue box. And so we can say, well, we focused element B4, good to go. Every cell is a slot which holds some A. In this case, they all hold numbers, roughly. Views can be relative, actually. If you want, you can look at the current context that you're at and say, oh, I want to move one column to the left, or I want to move one row down. But you also still can have an absolute view of the whole thing. And when we extract, we just get the focus cell. Yeah? Questions on this? It's pretty cool. Non-empty lists are another tree-like structure, right? So it looks very much like a stream, but it just might end at some point. That's fine. It just means that the subtree of that element is going to be nothing. But it's still the same as a stream. We say every element is a slot. The views are the list tails, like the tails function. And you know, we just pull out the head of the list. Yeah. Yeah, that one's really fun. So the really rough intuition, we can talk about this a little bit more in depth later, is that when you duplicate a spreadsheet, you put an entire spreadsheet into every cell, but remember the laws, when you duplicate that spreadsheet, the spreadsheet that you've put into cell A1 has the focus changed to cell A1. And the one in A2 has the focus changed to A2, so that if we extract, we get the original spreadsheet. Yeah. So conceptually, we're just like cramming all of these spreadsheets into another spreadsheet. Cool. So zippers are also kind of the comonad that, you know, there's blog posts about, people talk about. And it's because it's pretty cool. It's got good performance benefits in certain cases. But this is another one of those cases where, like, this is kind of a different version of the list comonad. That's, it still works roughly on lists. You do need a new data structure for it, but it can do different things. So in this case, the elements are the slots, like usual. And the views are doubly linked lists rooted at that element. So from the middle of this list, I can see earlier in the list, and I can see later in the list, and I know which is which. That's important. When we extract, we get the focus of this list. And when we duplicate, what we do is we actually say, OK, I'm going to put a zipper in each of these slots. But the zipper is going to be focused on the slot that it's inside. So the duplicated thing inside this A will have this focus of the doubly linked list on A. Same with B, same with C, etc. Cool. Functions are comonads in certain cases, not always. This is a really cool one, and this is probably what most of this afternoon and tomorrow is going to be about. I say here, star, when paired with an x value, we need to have some starting position. We need to know where we are. So I'm saying we're here, and we're at x equals minus 1.2, my favorite number, where every single position on this x-axis is a slot. It's kind of continuous, so it's a little tougher to think about, but there's no problem with that. Some functors are continuous. The function functor is continuous, etc. And the views are relative to your x. So you can think about, oh, well, if I'm here, then the left half of the function is this way, and the right half of the function is this way. That might mean something for your computation. It might not, who knows? And we can always get the y at our x. So if we say, oh, what is the y at, thank you, at minus 1.2, someone get a delivery? I don't know. Then we can say, oh, well, at x equals minus 1.2, we have a y of, 4.5 or whatever that is. Questions on this one? This one's a little bit confusing. We're going to spend more time on it soon. Yeah.
Extract gives you the y at your x. Does that mean it has to be a function from x to x paired with an x?
No, it doesn't. You can have a different type as your output of the function than you have as your input. Yeah, that's a great question. Okay, so let's also look at some things that aren't comonads, just so that we don't get too carried away and try and do this on everything. Lists. So there's the separation in base between non-empty lists and lists. Lists kind of have the idea of duplicate, right? Like you have this tails function, but you can't always extract. It will be partial on an empty list, and so we don't say that they're a comonad. But non-empty lists are a comonad. Great. Functions without the x value, well, how do we extract? We don't know which x you want, right? There's no way to decide which arbitrary x the user wants. I/O, it's a context, but we can't pull things out. So most of these, the most common law to be broken is the extract law, that we have this function that we can pull things out of any version of this type.
I don't know, I'm a Scala programmer, but I guess you have something like unsafe from I/O. On I/O, when you extract actually value from an I/O, right?
I'm not going to bother even addressing that. It had unsafe as the first word. All right. Cool. So we have this maybe in either. Both of these are sum types. And one of those portions of the sum type doesn't have the A. So what do you do if you have nothing? Well, you do nothing, because you can't.
A monoid constraint on the type inside the maybe. Could you
So just like a monad, the way the class definition works, you actually don't have access to put constraints on the internals, right? You're not allowed to say, oh, this is a monad where it contains a monoid. It's just not something that because otherwise it would make lose the generality. Yeah. Very good thought. Cool. Any questions about things that are or aren't comonads? You can think about this one, and during the...
Something like, let's say I/O has this unsafe word attached to it,
Yeah.
which we aren't going to use. But let's say we have a moment, like a future monad.
Okay.
Which says there's a computation which will yield a value later on.
Yeah.
Then if is it a comonad, we can just wait with some timeout for a value to appear, possibly infinite timeout.
Right. So...
That will be our extract, right?
So yeah, so that's kind of a side-affecting thing, right? In most languages, to run a future, you need to run it in I/O. And if you have to wait, you can't extract immediately. When you want to extract, you want to extract now.
But is it observable in a way? I mean, you don't know what is now, right? You just call extract, and it will yield a value. You aren't aware of time.
Yeah, so...
Is it anywhere in the laws or,
Okay, but in Haskell, at least, which is what we're talking about right now, all of these future types actually run in I/O. So you would end up in I/O, and then you can't extract further. So
Your structure, is it a good comonad?
in general, it's not a comonad. I don't know that if you can make an isomorphism from this future to an identity type, then you have a comonad. But until you can do that, then I would say no. Let's see just how much time we have, how much stuff. Yeah, okay, so we do have quite a bit more, but we'll leave that for after the break, I think. We have 1 more minute for another question about is it a comonad? Okay, cool, I'll let you go. You can think about that during the break. Maybe we'll go from there. Thanks for listening.